Welcome back. And right now we're going to do we're going to switch gears a little bit and take a look at this multiple output example. So this is a BCD to 7 segment converter. This is something that you should pay attention to because lab number 2 is going to be a hexadecimal to 7 segment converter. So on your board, you're going to have actually 4 of these side by side. This is for lab number 2. And when I say for your board, we're getting a whole bunch of boards from Digilent. You will have to show, if I want to show the character 1, for example, this is an easy one. Character 1 consists of element B and C to be 1, starting with A, B, C, D, E, F, G. That turns out to be 7, right? So that means if this were 8-bit, you would have to pad on to the front. So when I have B and C, then this becomes a 1. These are lit up. If I have the number 0, that means I have everything but G lit up. So A is 1, B is 1, C is 1, D is 1, E is 1, F is 1, G is 0. So with that in mind, what sort of digital logic do we put inside of here that will convert this input number to this converter? And it would probably be helpful to know this is WXYZ. So in this case, if we have WXYZ and we have the value 0, 0, 0, 1, that would be converted into this right here. So we could display the character 1. Now to do that, you could start with the table. So in other words, the value of 0 is going to be 1, 1, 1, 1, 1, 1, 0. All of these lit except for G. Or for example, this is 1, 0, 0, 0, which is the decimal number 8. And so that would be lighting up how many of them? Every single one of them, right? So an 8 has all of these lit. So 8 is 1, 1, 1, 1. Oops, where'd it go? There it is. 1, 1, 1, 1, 1, 1, 1. 9, you notice here it is everything lit but element E. So here's 9. A, B, C, D, E is not lit. F, G is lit. Now notice here, 10, 11, 12, 13, 14, 15, they don't really exist, do they? Correct? Yes, no? In binary coded decimal. But what if we're displaying hexadecimal? So if I were to do that, maybe my display thing down here would be F displayed like this. Does that conflict with any number? So what would this row right here be? Am I lighting A? Yes. B? No. C? No. D? No. E? Yes. F? Yes. G? Yes. There you go. We have now just done some of the problem associated with lab number 2. E, what do you think that would be? Well, that's easy, right? This is 2 segments, right? So everything is going to be lit except for B and C. So in this case, it's going to be 1, B and C is not lit, D, E, F, G. You could figure out the rest. I believe A is going to be easy. Oh, what about B? Because, you can't do all these because then it'll look like 8. So in B, what we do is we do the lowercase. C, we'll just do the full C. And then D is the other one that's kind of funky. Because, see how this B, it kind of looks like a 6, but not quite. So a D is going to be like that. Because otherwise it's going to look like a 0, right? So now you know what it all does. So I guess the question comes down to, how are you going to represent this in a Boolean equation? Well, that looks like it's a whole bunch of ands, right? So maybe to display, hold it. But what are we looking at? Are we looking at going across or are we looking at going down? Because we're going to want some logic to go in here and say, do you light up A or not? So what way can you do that? Well, let's look at an example. So you could light up A by saying, which situation are these 1? 1, 2, 3, 4, 5, 6, 7, 8 situations. So we should have 8 terms. 1, 2, 3, 4, 5, 6, 7, 8. Pretty easy, right? And actually that representation for B, you would do the same way because it has how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 elements as well. And so on and so on. So if you were actually to look at this, you would have a pretty complex equation for all of these. Is there a way to simplify it? What do you think? What's the way to simplify this? A K-map. That's the easy way. So here's what I want you to do. I want you to, let's see, I'll erase all ink on the slide. I want you to do a K-map, but I want a change. This is going to be A, B, C, D, E, F. So let's change this to work with lab number 2. So is A lit up? Yeah, that'll be lit up, right? B, no. C, yes. D, no. E, yes. F, yes. I want you to represent the logic needed to light up A in a K-map and then minimize. Take a few minutes to do that with a neighbor next to you. All right, so getting back to this problem, again, we started with this. Specifically that column, we put it in the lines. Now one thing to note is this is the first line, this is the second line. Remember we swapped these two in your K-map, right? This is your second line, this is your fourth line, this is your fifth line, or third line. So the representation I have for that is this. Do you agree with that? Yes? All right, now, when you're making K-map circles, one thing to note is that you want to bunch everything as much as possible with like type units, all right? So this 1 right here, it can't be combined with anything this way or this way, so you have to go this way, and it turns out that you can circle those 4 right there. So those would be such that x is equal to 1, and since we're doing since we've circled 4, then we could take another one. In this case, it's y. All right? So this box right there is xy. Now notice that this 1 right here can't be combined below or to this side. So we have to go, oh yeah, we can wrap around to this way, and we could wrap around to this way. So this 1 can be combined such that we now have, what is this? Oh, it looks like, what changes? X is going to be not. And what else? Well, Z is not as well, so Z not. Okay? Now, can we grab any other blocks of 4? Well, this one right here, we can't go up or down or to that way, so that's going to be a block of 2. We'll address that later. This one hasn't been grabbed yet. We can't go that way to the left. We can't go to the right, so down there. So we can actually absorb it right here. So in this case, it's W prime, and representation here is Y. All right, any other 4s we can grab? Oh, here's one right here. Can't go up, can't go to the right, but we can go down and to the right. So we'll combine those together. That turns out to be, in this case, W and Z prime. Now we have 2 lonely 1s left, and so to get them included, you're just going to have to circle 2. So in this case, it turns out to be W x prime, and then in this column it's going to be Y prime. And then finally, to grab this one, it's going to be W prime x, and then this column, these 2 columns are going to be such that it is Z. So your function for the character A is going to be equal to this set of equations, 1, 2, 3, 4, 5, 6. Now, if you were to do this with gates, this would get really, really, really messy, wouldn't it? So you're going to really appreciate being able to type this in as a formula in VHDL. Question?
I completely got lost. I don't know where you got the 12 terms from that were true. That's actually where I got lost. Okay,
well, the 12 terms. Let's take a look. So if you look at the table that we have here, do you agree, and we're doing this again for the hex to BCT, or hex to 7-segment converter, do you agree that A, B, C, D, E, and F, the characters A, B, C, D, and F, will light up this little element A right there, just this little segment, by putting a 1 here? Do you agree with that? Because if you look at A, again, I said, is 1 across the top, down, down, over, down, down. You agree with that? Is that yes or no?
Shouldn't just be A the one that lights it up?
Remember, there's a difference. This is the character A that will light up here. And lowercase a just is that particular one single element right there.
Okay.
You got that part?
Yes.
Okay. With B, notice it's not lit. That really top little element right there is not lit. C, it is, because C is over, down, down, over. So that is lit, so I put a 1 there. D is not lit, E and F are lit, then we get the 1, 1. You got that now? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we go back to our table and we count out the number of 1s, yeah, I could just take 16. Yeah, I'm moving the mouse. It's not showing. 1, 2, 3, 4. 4 zeros. All right. Wow, this looks like this would be an awful lot of work because we have the little segment A, then B, then C, then D, then E, then F, then G, right? So this is a good example of needing code to do this. But there's another sneaky thing. When you're using a code package like VHDL, you actually can, and by the way, for this equation right here, for the hex to BCD, we would have to add those 4 elements there too. Remember? You agree? Is that yes or no? Okay, I have a couple of heads nodding yes, and I got some people who aren't necessarily doing it. So we will do these. What do I need to add on to here? What is this? W, X prime, Y, Z prime. Ah! That's a Z, can you tell? All right, WX prime, Y, Z prime, plus the one for this, the one for this, the one for this. But I'm not going to go on because you could figure that out on your own. Now in VHDL in our lab, you can actually just type in this entire formula. And the tool will actually do the minimization itself. Easy enough? You're just going to have to make sure to put it in right. But you know what? That's easy to do, right? Now, let's talk about how you would do a design, a digital design. And that's actually when we're talking about the design process. So the first thing is to capture the behavior. Create a truth table or equations, the most natural for a given problem. In other words, you're going to have to identify the correct way to identify what the function is. Then step number 2 is convert to a circuit. In other words, you only have to do 2A is if you captured the function with the truth table. Well, that's the first step, right? What is this going to look like for our hex to 7-segment converter? And once you have that, then you would have to write out all the equations. That would be step number 2A. And then for each output, create a circuit corresponding to the output's equation. Sharing gates among multiple outputs is okay. So let's take one example. Oh, and then let me go a little bit further too, and that is when you are doing an exercise for this lab. Remember, I mentioned that you are going to have and again, this is for lab number 2. You're going to have 4. Oh, I zoomed out. So or zoomed in. You're going to have 4 of these whatever segment displays, right? You're also going to have a total of 16 switches. These are slider switches. You know, when they're down, it's logical 0. When they're 1, they're logical. It's logical up. So, what's one thing you know for sure about this? You know that that is associated with these 4 switches, correct? You agree?
Yes.
What about this one? It's going to be associated with 4 switches over there, right? But what do you know about this functionality and this functionality? Are they the same? The code, the execution is going to be pretty much close to the same, right? So the answer is maybe you can get one of these things working correctly before you start copying it to represent this one and this one and this one. And this is an iterative process as well. So not only did we show you, start with a truth table and then convert to an equation and then build the hardware from that, but in situations where you have identical type of functionality, just kind of like a little bit different of what the input is going to be, like it's this switch here instead of this switch here, you should get that working first before you cut and paste anything else, right? And now I'm even going to go a little bit further, is when you are designing, wouldn't it be good to verify the following? Maybe you want to, 1, start with segment A. And what are those situations when segment A is lit? Well, segment A is lit for what values of, what's hexadecimal values? So, hex values 0, 2, 3, not 4, 5, 6, 7, 8, 9, A, C, E, F. So what you would do is you would start your exercise and you would only write in the equation for segment A. You would go through your build cycle that you've done already, right? And you know what? You could simulate this before you put it on a board. You would simulate it to make sure that, with the inputs that would be represented by these hexadecimal numbers, and make sure that A actually is output in the right way. So you get a little bit of a flavor of how to work with it. Then you would add segment B, then you would add segment C, and debug each of those to make sure you entered in the equation correctly. And then finally, when you got all of the equations in the appropriate way, then you would be able to transfer it to the hardware after you have simulated it. Now, one thing I should add is that lab number 2, I am not sure if we're going to be able to get to the hardware, because right now I only have 10 boards in my hand. I'm supposed to get another 20 on Friday, and I'm working with them to get another 30 by the Friday after that. I may not get them in enough time, so lab number 2 may be another simulation lab until we get the actual hardware in. But it'll be the same concept. The same concept being you will have inputs W, X, Y, and Z, and then you will have the segments that you will light up, A, B, C, D, E, F, G. So it's the same idea. But at least you'll get some flavor of working with the particular devices. All right. With that done, let's go on. Let's look at the example. Let's say we want to have an exercise where we identify if there are 3 ones in a row. So we have 8-bit, A, B, C, D, E, F, G. So it's easy to see, would you agree, that you need to have it such that A, B, C, D is 1, or B, C, D, E is 1, or C, D, E is 1, or D, E, F is 1, or E, F, G is 1, etc., etc. So we know from this that we could have pretty much a simple equation, right? The truth table is too big, but it's obvious if you want 3 next to each other, there are only these 6 situations out of the total of 256 where actually there's more than that, but they simplify out. So now that we know that, you can easily design your equation, already done, but now let's do it as the gate-based circuit. So obviously we have a whole bunch of 1, 1, 1, and them together with an OR gate. So we have 3 input AND gate, and we have a 1, 2, 3, 4, 5, 6 input OR gate. Well, let's just assume that we have that hardware available, and so our circuit would look like this. Notice we don't have to worry about any NOT gates because it's all when A, B, C, D, E, F, G, H are 1s. And that's how you would follow the step for that. How about to count the number of 1s? Well, in this case, you're going to have a situation where you have, well, in this case there's 1, in this case there's 2, in this case there's 0. And so the equation would be to count up the number of 1s. So it looks like the truth table would be relatively easy to identify because you would have, in this case, counting up the number of 1s, you would have A, B, C, multiple inputs, multiple outputs. Remember, we've seen an example where you can do that. And then you could convert this into the equation. The equation being we have, for Y, we have 1, 2, 3, 4. And in Z, we have 1, 2, 3, 4. We can simplify, so Y simplifies a little bit. And if we wanted to see, and by the way, X doesn't simplify, or Z doesn't simplify at all. And in this case, we're going to be lazy and not put the actual NOT gate there. But we couldn't fit it on the slide, so we'll put that there. Now, in the previous example, you can simply draw this like this, AB, even though A and B is up there. You could just do it without having to draw these extra wires. And you know what? Somebody came to me about this NOT gate. I tell you what, I'll just say, if you put the bubble there, that's okay. I'll let Lauren and made sure to turn off the microphone so I didn't sneeze in it. If you put the bubble there, I'll allow it. So since the book allows it, so come to me, see me about this after class on Thursday, not today. Here's another example. Let's say we have a keypad converter, and if we press a 1 here, we'll get a 1 show up here, and we'll also get a 1 to show up on C1. So if we have a situation where we have R is 1 and C1 is 1, then we'll display W, X, Y, Z. And then if nothing is pressed, then we'll just output 1, 1, 1. So we're going to capture the behavior. Truth table is big. Equation's not clear. So some sort of informal table will help. So in other words, keep in mind that we're going to assume that you're not pressing multiple keys at one time. So for that case, you know, when you're pressing button 1, that's R1, C1, your output is going to be Z, etc. This will show the rest of the situations. From that, we can get an equation for W, X, Y, and Z. Looks like a lot of work, doesn't it? Now notice that this last one can't be simplified. When you're pressing nothing, that means that R1, R2, R3, R4, C1, C2, C3. Why is C4 not pressed? Oh, because we only have 3 columns, sorry. And the same for W and X up here. So with that, I will, let's see how close is this. With that, I will finish this example in our class on Thursday. Thank you very much.